So I was saying in this case that normally the process of collisions involves very short duration of interactions compared to the duration over which the bodies move. For example, if we just look at the collision of two carom coins on a carom board, we strike one of them, it goes and hit the other one. That interaction happens for a very short duration compared to the time over which the body, this carom coin are moving. But again, that short is the relative time over there. We might have, for example, collisions to galaxies, for example, like the Andromeda and the Milky Way. They are in the course of collision, and they will collide during the, it's the next 5 billion years. That's what is said. But this collision will take quite million of years actually. So that is the relative notion. Obviously, million of years will be more than many lifetime compared for humans actually. But over the duration on which these two galaxies are moving, that will take place very shortly actually. There is also a collision, and two carom coins colliding is also collision. These are taking relatively small time compared to the duration over which the bodies are moving. So that is a requirement actually. Okay. Obviously, we can have collisions without impact, without touching as well. Like in case of carom coins, they will definitely touch. Only then they will exert force on each other. But we might have, for example, collisions between two positive charges, like one magnetic. Yes, we can have magnetic as well. We can have electrical as well. We could have gravitational as well. Actually, uh, there's a term which is used in it's the space sciences by the way, which is called a gravitational slingshot. Have you ever heard of it? Gravitational slingshot. The idea is to utilize the gravitation of some heavy planet to increase the speed of the rockets, for example, or the space probes. For instance, the space probe known as the New Horizons, which was launched to study Pluto actually. If we send it directly to Pluto, the fuel required will be quite large. But what was done is to make use of the gravitation of the bigger planets. It's almost like collisions basically. There's a Jupiter. Jupiter is there, so the slingshot, the space probe basically just comes this way and then slingshot like that. It's pretty much like a collision actually, though it's not happening kind of head on, but nevertheless it is a collision, and that collision will basically it kind of increase the speed of this small bodies manifold actually. We shall see later on that when a smaller object collides with a bigger one, in that case, in effect, assuming elastic collisions, in effect, the velocity of the bigger one is just added to the smaller one actually. So something that happens, Jupiter is moving up to the high orbital velocity that was being added to the speed of the this small probe, and that is an example also of collision. Basic, we shall obviously not talk about the Jupiter collision colliding with this space probe, neither the collision of the Milky Way and the Andromeda over there, but mostly we shall be talking about collisions of particles, which more often than not, they will just interact with using a contact force. Contact interaction is going to be there, but that is going to be very, very short duration compared to the overall time in which the two bodies are moving. That is a basic requirement actually. Now, turns out in this case that the analysis of collisions, it can be done much more easily using the momentum conservation and which planet? Well, actually, on bigger planets can be used, Jupiter or Saturn, even the father planets like it's a bigger one, which is bigger. Neptune is bigger, I believe. That can be done as well. In fact, for smaller space probes like Venus can be also used because that is too small, but Venus is within the Earth. But we can just go outside towards the outer side. Outer side, we can use Mars as well. Anyone which is, for a space probe, quite obviously, any planet is quite small, big actually, so it hardly matters over there. But usually the bigger ones are used because it's much easier to kind of deal with the trajectories then actually. Inner planets don't, obviously we don't require to use them, only the outer planets. And outer mostly they are bigger compared to the Earth. But speaking in a strict manner, it can be anyone can be used actually. It is almost like you take a ping pong ball and throw it to a moving truck. While the truck is coming towards the forward direction, and throw it over there. No, it doesn't matter actually on it. Well, it might matter for the instruments which are on board, but usually that is not a problem because well, some kind of shielding can be done. I don't think that magnetic field will have such an impact because the body is not overall charged actually. It's going to be only important as far as the motion is concerned. Obviously, the electronic circuitry might be affected, but as far as the motion is concerned, it is only going to be a problem if the body was charged overall, which it is not. So it is not going to be much a problem. But Jupiter is definitely used. Anyway, what I was saying is normally the analysis of collisions can be done much more easily using the momentum conservation considered to the dynamics themselves. The point is that because interaction takes place for a very short duration, in general, we need not actually look at the forces because more important than the acceleration, what becomes important is the changes in the velocity because it is almost happening abruptly. So it will be much useful to consider the changes in velocity, therefore the impulses. The other thing is that when two bodies interact, they usually, in a collision, they exert large forces for relatively short duration of time. So what happens is, if I look at the impulses of the colliding forces or collision forces, for example, on one body, the impulse exerted by the other body, if I consider on one of the objects, the force with the other one. If I look at that, normally it will be very, very large for a very short duration of time, starting from zero. I'm assuming that the collision starts at t equal to zero. It will just happen to be very large, but for a very short duration of time. This is in this case a duration of collision. Let's call it delta t, which is quite small compared to the overall time of motion. But the other forces are also present. The finite forces, like the gravity, might be there. And if the collision is taking place between two bodies moving on a rough surface, for example, in that case, we might have friction as well. Not their mutual, but with the ground actually. But those forces are, in this case, are example of finite forces. They are relatively small compared to the colliding forces actually. So if I look at the other forces, for instance, they may be, for example, like this, like gravity is present, it will be just a small value compared to the colliding forces actually. So if I look at the impulse, the area under the graph of F and T, you find that the area occupied by the red graph is quite small compared to the area of the blue one actually. So what happens is therefore the impulse created by the finite forces on the body is negligibly small compared to the impulse of the colliding force. And for that reason, most of the cases, or at least if the I mean say the other finite forces, they can be neglected on the body, on the system as a whole, which implies that even if there is an external force present, we can still conserve the momentum just before and just after the collision because the time duration is very small. And the other force, the external one, they will hardly affect the momentum. They obviously will affect over a long run by the, say, for a larger duration of time. But during the impact, at least, which happens for a very short time, we can simply neglect those finite forces. That also present a case where we can actually apply the momentum conservation even though there are external forces present. It happens so because the forces apart from the collision one, they are more or less, say finite forces. Obviously, we might have impulsive friction as well. For example, if if one body is thrown on the ground at an oblique angle over there, in that case there will be friction present as well. In which case that friction is also going to be impulsive. Then we can't neglect that. That will also affect the final velocity, in fact. But At least when two bodies colliding and there are finite forces, then you can simply neglect it. Okay. So the main tool that we use for analysis of collision is the momentum conservation, and there's one more, which is known as the Newton's law of collision. Actually, with these two tools, we can actually analyze uh, most of the collisions. At least two bodies collisions can be easily analyzed by using these two.
Sir, here we don't use the law of conservation of sorry. So work energy principle, law of conservation.
That may not be applicable. You can obviously use it, but whenever there's collision, for example, an inelastic impact where the energy is lost, we do not know exactly how much energy is lost actually. That is why we can't apply most of the time the energy method. If it is specified to be um, elastic collision, then we can. But what I find much easy is to use the momentum and the law of collision actually, because they will involve linear equations. If you bring the energy into picture, they'll automatically bring the quadratic actually. So it's much more difficult to analyze the quadratics compared to analyzing linear, isn't it? Obviously, if the collision is elastic, you can apply that. But normally, I would prefer to use the other two, the momentum conservation and the Newton's law of collision actually. With those two, I mean, say with some extra information like the coefficient of restitution kind of thing, we can tackle most of the collision problems, which are at least two bodies problem. They can be done in this case. Okay. Obviously, if it is specified, then we must use energy, but otherwise, I'll try to avoid it. Fine. Let's see an example. The idea is what we first of all take up the collisions between two bodies, which happens to be head on, which implies first dealing with a head on collision. In a head on collision, the body, the two bodies, they are moving, and the velocities are along the line which join the centers actually. That's an example of a head on collision. The velocities are along the centers of two bodies. That's head on collision. So we just consider also the bodies as point objects. Say, for example, that we have, before going over there, there's one more tool that I was saying. Look at the Newton's law of collision. Or you can, this is an empirical law actually. It is not again coming from some theory, but it's more like an empirical thing, which is found to be experimentally valid actually. The result says that when two bodies collide, again a head-on collision talking about, or at least it is true along the common normal, implies along the line which join the two centers, even if the collision is not head-on but oblique collision, even then this will be applicable along the line which join the two centers, which implies on the common normal actually. So what it says essentially is that along the common normal, when two bodies are coming and they're colliding, then we just talk about the velocities before and after the impact actually. So in the common normal, the relative speed of separation, relative speed of separation is equal to this number E times the relative speed of approach. That is Newton's law of collision. It says that along the common normal, which implies along the line which joined the two centers, at least for point particles, it will not be an issue. There'll be point objects, so we can always join them, and we end up getting the line which join the centers. Along that direction, if you look at the relative speed of separation, implicit is the fact it's after the collision actually. This relative speed of separation, sorry, it will be after collision. While relative speed of approach before the collision is what I have. So the idea is that the bodies, whenever they approach with certain, this is the relative speed. By the way, notice it's not velocity I've written down.
So approach only means before the collision.
Again,
So approach means before the collision.
yes, but I still specified it, so there's no point of confusion actually.
Oh.
Okay. But you should notice that these are talking about the speeds actually, not the velocities. I've written down the speed, so we need to see the relative speed of separation and the relative speed of approach actually, which implies that if the two bodies, obviously if the two bodies moving towards each other, in that case approach to be speed will be simply the sum of two speeds. But if they're moving away from each other and then colliding, for example, one is going towards the right direction, the other one is also following it and then colliding with this one, moving the greatest speed actually. In that case, the relative speed can be obtained by subtracting, isn't it? But you must notice these are the speeds and not the what do you say, the velocities actually. Okay. E in this case is known as the coefficient of restitution. This E that you have written down, this is called the coefficient of restitution. It is a number which has to be experimentally measured for every pair of bodies. For example, steel with steel, steel with wood, or ivory with wood, and so on. For each pair of bodies, this need to be figured out, and this will be given quantity in most cases, unless until it is figured out actually. Usually, when E is 1, that is referred to as a perfectly elastic collision. If I consider normally this number E lies in between 0 and 1. If E is equal to 1, that's a perfectly elastic collision. While if E is equal to 0, that's a perfectly inelastic collision, which are both extreme cases actually. So we can definitely have perfectly inelastic collision, but perfectly elastic collisions are difficult to come by.
Sir, can you please repeat what is coefficient of restitution?
This E, that is, we have written down the ratio of the relative speed of separation and the relative speed of approach. That ratio is called the coefficient of restitution.
Okay,
Or the proportionality constant, you might say, that the proportionality constant by which the relative speed of separation is determined from that of the approach speed actually. That number is the coefficient of restitution. It is quite obviously going to be less than 1 because relative speed of separation cannot be more than that of approach unless until there's some explosion taking place within. That's a different story. So for E equal to 1, we have perfectly elastic collision, which is in most cases, I mean, we shall be dealing with that, but just for the sake of completeness, we need to know the other cases as well. E equal to 0 is a perfectly inelastic impact collision, while most of the real life collisions, they are in between them actually. So you can simply call them as an inelastic impact or just an imperfectly elastic collision, what we might say. But in most cases, E will lie in between 0 and 1 actually. Okay, that's right. Fine. With this particular these two statements, we can move over to the analysis. Say, for example, we consider I've rubbed it up. Hopefully, people have to take up in this case two bodies. Again, treating them as point objects and taking them in terms of head-on collision. We have in this case 2 point masses. I'm showing them moving in the same direction. But the idea remains the same. So we have a point mass m1 moving with a speed of u1, and on the same line, there's another point mass m2 going upwards, moving speed u2, and these two particles they collide because u1 is greater than u2. So ultimately, after some times, m1 tries to overtake m2 and they collide. The resulting collision produces velocities of these two after the impact as v1 for m1 and v2 for m2. These are in this case the velocities after the collision. Initial ones are u1, u2. Our task is to figure out v1 and v2 in terms of u1, u2, m1, m2, and the coefficient of restitution between them. Okay, so assuming in this case that the collision is not perfectly elastic, so the coefficient of restitution E is a known factor that we shall assume, and we would like to in this case find out v1 and v2 in terms of the other parameters. Because in this case, I mean, we have what I was saying. Yeah, what I do is in this case, first of all, take a system suitably which consists of these two particles together, these two together. If I take them together into account, then during the impact, as I said already, the finite forces can be neglected. So even if there are some external finite forces like the friction or gravity, we can simply neglect them and just conserve the momentum just before and just after. Because in this case, these two bodies within the internal forces will cannot affect the momentum, and the external forces are negligibly small. Therefore, the momentum remains conserved. The first equation we can get it by conserving momentum because everything is moving towards the right. So I'll write in this case the velocity components rather the momentum components towards the right. We end up getting the first equation that m1 into v1 plus m2 into v2, which is the final momentum of the system just after the collision. This has to be the same as the initial one, which is m1 u1 plus m2 into u2. This is the initial one. Okay, that's the first equation we've got. Because we have two unknowns v1 and v2, we require one more equation. This comes from the conservation of momentum. I'm writing conservation of momentum. And the second equation will come from the Newton's law of collision. So second equation, law of collision is what I have. The word gives, first of all, you notice that after the impact, the separation speed becomes v2 minus v1 because they can only separate if v2 is larger compared to v1. Therefore, the relative speed of separation after the impact will be v2 minus v1. I have v2 minus v1 as the relative speed of separation. According to Newton's law of collision, this has to be e times that of approach. Now, what about the approach speed? They can approach towards each other obviously only if u1 was more than u2 in our scenario. So the relative speed of approach has to be u1 minus u2 because they must approach, otherwise there won't be any collision. If u2 was greater than u1, they won't collide. Okay, and therefore these are two equations we've got. They're both linear equations and easy to solve. Our task, as said, is to find out v1 and v2. So let's first figure out v1. For that case, I notice that if I multiply the second equation with m2 and subtract from the first equation, then v1 survives, v2 cancels out actually. So what I do is I multiply the second equation with m2 and subtract from the first equation. So in that case, m2, v2 will cancel out, and this becomes plus m2. So I end up getting in this case m1 plus m2 into v1. That must be equal to, we already have m1 u1, and there we have m2 e into u1. So I'm just going to get m1 minus e m2 into u1, and then we get m2 u2, and this becomes plus e into m2 u2. So I end up getting over there 1 plus e into m2 into u2, as we have, and then we can just divide by m1 plus m2 to end up getting the velocity v1. So v1 turns out to be m1 minus e into m2 into u1 plus 1 plus e into m2 u2 divided by m1 plus m2. That is the velocity of the first body after the collision. m1 minus e m2 into u1 plus 1 plus e into m2 u2 divided by m1 plus m2. Looks complicated. The point is, we need not derive this, we need not remember this equation. It's just an easy matter. We have two equations, write them, simplify them, solve them. It just happens in 2 steps over there. I don't think therefore there's need to remember this. What about V2? We can obtain V2 by simply interchanging the indices 1 and 2, because the problem is symmetric with respect to V1 and V2 actually. Whatever I have called V1, I could have called them as V2 as well. So V2 can be obtained by simply interchanging the indices 1 and 2 in this case. Wherever it's present, this becomes V2. This becomes M2 minus EM1. This is U2. 1 plus M1, 1 plus E into M1 U1 divided by M1 plus M2. That is what we end up getting for V2 actually. If I consider, I'm not writing down, let me write down. This turns out to be V2, the velocity of the second body. As such, they are again seems quite complicated over there. There's hardly anything that we can deduce from here. But in some special cases, we might see a couple of things. For example, if I have first of all a perfectly inelastic collision, for example, if I consider that the collision is perfectly inelastic, in that case, let's say E is equal to 0, for example. That's a perfectly inelastic collision. You notice that because E is 0 in a perfectly inelastic collision, from the definition of E, we find that the relative speed of separation becomes 0, because it was E times that of approach speed. So E is 0. So I get the relative speed at which the bodies separate after the collision is simply 0, which implies they don't separate at all, which implies they're moving the same velocity, or you may say that they have stick together actually. That's what happens in case of an inelastic collision. The bodies, they simply do not separate, they just move together as single object. You might think of, for example, a ball of dough, the one from where chapatis are being prepared. If you just use that dough, the ball of that dough, and then throw it on a wall, for example, it sticks to the wall. That's an example of an inelastic collision. Perfectly. It will be slightly imperfect, but most cases it looks like a perfectly inelastic impact actually. So such a situation, if I consider E equal to 0, you can see from this V1 and V2 that E is 0. This part gives us M1 E1 plus M2 U2 by M1 plus M2. Well, this part also gives the same thing, M2 U2 plus M1 E1 by M1 plus M2. So that implies they have the same velocity which is to be expected because they're not separating at all. So I get this. That becomes the case when E is 0. The collision is perfectly inelastic. If on the other hand, if consider, say for example, E equal to 1, that's a perfectly elastic collision. In this case, what I get? If E equal to 1, then I have V1 as M1 minus M2 into U2 plus twice, U1 actually, plus twice M2 into U2 divided by M1 plus M2. That is V1 in case of perfectly elastic collision. And if I look at V2, that becomes M2 minus M1 into U2 plus twice M1 U1 divided by M1 plus M2. That's what's happening for E equal to 1. Again, this is hardly anything that we can think much about. It doesn't give us much information, much insight from these equations. But a couple of special cases can be considered, which again gives us some, I must say, interesting insights. First of all, we notice that if it happens that M1 is equal to M2, if for example M1 is equal to M2, what happens then? If M1 is M2, they are identical masses. You notice in this case that over here this part will become 0 and M1 is equal to M2, so let's put both of them as small m. This part becomes 0, this part becomes twice mu2 and this becomes twice m. So 2m gets cancelled out. We end up getting in this case
V1 equal to U2.
exactly. V1 becomes equal to U2 and similarly V2 will become equal to U1, which implies therefore that in case of a perfectly elastic collision between two identical bodies, identical imply identical masses actually. So when two bodies of same mass collide with each other in a elastic fashion, then what happens is along the common normal they exchange their velocities, which implies effectively that when two bodies consider when two bodies of identical masses collide head on, two bodies. They collide head on perfectly elastically. Then they exchange the velocities. That's it. As we have for the case when two identical bodies collide, they simply exchange the velocities. On the other hand, if I look at some other cases, for example, if I take up what happens, for example, when a massive object collides with another very small object, which is say practically at rest, or you can just consider the collision of a ball with a wall, for example. We just throw a ball onto a wall, assuming perfectly elastic collision, we expect the ball is going to rebound back, isn't it? That is what we can expect in this case. Say, for example, that M1 is very light compared to M2. Then let us see what happens if M1 is very, very small. M1 is the incoming mass, actually, the mass which is moving towards the other one. So if I consider over here, if M1 is very, very small compared to M2, what happens then? In this situation, we notice that because M1 is very small compared to M2, at least in this summation, M1 is negligibly small. So I could just neglect this M1 over here as well. So I get minus MTU1 plus twice MTU2 by M2. M2 gets cancelled out. I end up getting therefore in this case V1 approximately as minus u1 plus twice u2. These are the velocity components that we have. Negative 1 implies the opposite direction. So v1 is therefore turning out to be twice u2 minus u1. So first of all, if the massive object was stationary, then v1 becomes just nothing but minus u1, which implies if I just throw ball onto wall, it simply bound back with the same speed, which you would expect actually. But if the wall is also moving towards us, in that case, the velocity of the ball will be increased by twice u2. Okay, that's what we have. That is, in effect, the same thing which is utilized during this gravitational slingshot. Actually, you may imagine, for example, Jupiter is like a ball which is moving towards the ping pong ball or the satellite in this case. So, in effect, satellite gets rebound back, and then the twice the speed of the planet is also added up over there. Fine. So, we will get from here. While V2, what think about V2? If I consider V2, M1 is negligibly small, so this can be negative compared to M2. This becomes U2 by, M2 U2 by plus twice M1 U1 by M2 actually. If I consider this part V2,
Sir, in the one there will be a by 2.
where
7 M1 will be
this one,
than M2. Yes, sir.
no, actually what happens, M1 is neglected, M2 U1 is present with a minus sign, and twice M2 U2, and there's also M2 present. M1 is neglected, so M2 is the one which is present.
Yes.
So what I get in this case, the V2 will turn out to be, is visible. M1 is neglected, so I get M2 U2 plus twice M1 U1 by, oh, it's not, just try to go there. Approximately. That is to say U2 plus twice M1 by M2 into U1. But because M2 is massive compared to M1, this is very approximately the same thing as U2 itself, which implies the massive body hardly matters. That will just continue to move as it was moving. Nothing happens to that one. While the lighter one is basically rebounding with roughly the same speed if the heavy body is stationary, but if it is not, then twice the speed of the heavy body is also added up actually. That's what happens in case when we have a very light object colliding with a massive body actually. Fine. In this case, remember that we're assuming direction to be same, but if, say, for example, a light body ping pong ball is thrown towards a truck is coming this way. In that case, the velocity will be opposite, in fact. U1 will be that way, but U2 will be this way, in fact. So the direction of minus U1 and U2 will coincide in that case. And therefore, the numerical values will be just added up actually. So the ping pong ball rebound with a speed which is larger compared to what speed was moving already, in fact. Okay. That is what the idea which was utilized for slingshot as well. The Jupiter was coming this way, space probe goes that way and then comes back, returns. That's like a collision over there. So when they collides, it will come up with the twice the speed of Jupiter added to the speed of the space probe actually. Fine. So that is the usefulness in this case. The speed is increased without spending much fuel. This way, for example, for the New Horizons space probe, which was sent to take pictures of Pluto, roughly 80% of fuel was saved. In fact, had people tried to send that directly to Pluto, that one would have involved much larger amount of fuel compared to when the slingshots was being utilized actually. Okay, that's what the idea is. So at least obviously we can analyze the same thing. What happens, for example, if a massive body goes on to collide with a small body? Again, the same story. The massive body hardly anything happen. Well, a smaller one will rebound with double this with this whatever speed is coming up and twice the speed of the massive body added to that one. Okay, that is what happens. As I said, in this case, these results need not be memorized. You can always obtain them starting from the two equations that we wrote down earlier. The momentum conservation and the law of collision, actually. That should be enough. Yes, Chandrayaan 2, actually, they utilized strictly speaking, it was more like a gravitational slingshot from the Earth itself. It just went round and round. For example, this is the Earth, so it just utilized not the Earth. Chandrayaan I'm talking about. Oh, Chandrayaan was not something. It was a bit different. Chandrayaan doesn't require, but it did require suitable timing. Actually, I was talking about the Mangalyaan over there. Chandrayaan was not utilizing much of it. It just went around the Earth's orbit a couple of times. That it does involve the slingshot, in a different sense actually. But it just keeps on increasing energy by suitable timing over there, timing of the Earth's motion towards the moon or the moon's motion towards the Earth actually. That was obviously that is the way that people saved fuel in this case, but it was not strictly speaking a slingshot kind of. It was like more like you just know rotate, take up a stone, tie to a thread, and just rotate about the head and then throw it like those discus. So not discus, but hammer throw is there something like that actually. That also generates a speed enough. Enough. Okay. As I was saying, there's no need to, in most cases, remember the results, but utilize it directly, obtain it directly from the given data. It will be just taking a couple of steps. And just wait a moment. Got a book. Seems to be somewhere else. Anyway, I'll just find it. Let's take up an example which can be. Suppose that we have a 2 kg particle moving with say 5 meter per second and collides with another 1 kg mass moving with 3 meter per second. Assuming that the coefficient of restitution is visible, 2 kg 5 meter per second, 1 kg 3 meter per second. So assuming in this case that the coefficient of restitution is half, for example, determine the final speeds of both the bodies. I just bring a book and refill the pen.
So what is the question? Have to find the final velocity.
I seem to have misplaced the book. Somewhere I'm going to find it. Okay, I think the book on dynamics was being shared, isn't it? In the groups.
Yes, sir.
That is what I required.
So which page?
Well, wait, let me find it. There is a chapter on collisions actually. It's not in there, so that's pretty bad.
So the rigid dynamics ones.
Which one?
So the rigid dynamic ones.
No, there was a book on statics and dynamics. Statics and
So
dynamics.
are the answers 4?
4 meter per second, 5 meter per second. V2. Yeah. And 4, 8. Okay, it seems to be okay. Yes, let's verify it. Particle dynamics. That would be, oh, that's something else it does. Yes, I got the book. Wait.
Yes, sir. 4 meter per second and 5 meter per second.
Fine. That's okay. In that case, elements of there's something else. No problem. I've got the book over there, so figure out the page number. Yes. Okay. Some page numbers are missing. The one I wanted. 153. After that, we just get 156 directly. That page is missing. Okay, it's not. We are missing exactly what we wanted. Blue moon and red Mars. Okay, Anik. Is it empty or what? You have got that particular
So can you show me
page.
which page?
154 possibly. 154. It's coming up slow. Actually, this is a bigger one. Yeah, collision elastic bodies.
So then
Show that an elastic This is for this two equal. Yeah, I'm gonna say just scroll a bit up. Okay, before that, the page numbering is slightly different. Wait. Before this. This is an oblique collision. Before this particular exercise. Hold on. Again, it's oblique. Scroll up. Direct collision. Yes. Down a bit. This exercise. The glass, marble, rock. No, after that. Wait, hold on. Direct impact, yes. This is the exercise after this. Direct impact of two spheres. Go to the exercise after this section. What's happening? Again, the page is missing or what? 127. Before that, we are missing exercise. There has to be exercise in between them.
So I don't know that.
Well, I do not know. The book that I have, also the pages are missing. After 153, directly goes 156. You can read the question. A sphere of mass 4 kg
So
moving
this one.
5 feet per second overtakes a sphere. This can be taken up, but they're given in FPS systems. But yes, the questions can be. Okay, ठीक है, no problem. Let me just take once. I've got a different one, so maybe there is going to be. What is the page number you're saying? 131. Well, in that case, the same book it seems. Not an issue. You can just convert feet per second to meter. Just units as meter per second. The answer will be the same in any case over there. Yeah, ठीक है, no problem. Just take something else. It is not very readable, I believe. It's too small. Kindle edition. Collision of. Okay. Too many books you opened. ठीक है, okay, so not an issue. I've got the book over there. Fine. Let's see. This one is obviously done by all of you. It's not a difficult task. Anybody who is left and not finished this one? Or everybody has done? Done. Okay. Let's say next question. The question says there's a we have this, consider this one. E is half over there. Sorry, 3 by 4. If the question
So
restriction
I got it.
got it. Which one?
So see this.
Well, right now it is coming up, right? Yes, this one. That is what we want. Can you scroll a bit down? Yeah, yes, this one actually. This is given SI system. Yes, they have just changed numbers. Take a snapshot and post in the group. this page. The full page. Anyway, this question written down in any case. We have to figure out the velocity of the second ball. No, the first one. Well, both the velocities actually. In this case, we have to find out the velocities of these two objects. The first one moving with speed of u, mass m. The second one moving speed of u by 7, mass 2m. They collide head-on, and the coefficient of restitution is given as 3 by 4. We need to obtain the velocity of both the first and second balls after the collision. Okay. Okay, so it is posted. Fine. Just considered question 4 actually. That's what I did just now. So actually, we know the answer. By the way, the answer is that the first ball should come to rest after the collision. You got it, or not doing it?
Sir, u1 equal to 0 and v1 equal to 0 and v2 equal to 9 by 14.
Yeah, at least the incoming ball come to rest. That is known. And what were the other ones said? We just consider momentum.
9u by 14.
mu1 plus 2 by 7. That makes it 9 by 7. So, yeah, that's fine. 9 by 14 you is study, isn't it?
Yes, sir.
Okay.
V1 equal to 0 and V2 equal to what? Mine is coming 33u by 7.
No. It will be 9 by 14 u. Consider the momentum, right?
Okay, sir.
Momentum has to be conserved. Initial momentum is mu plus twice mu by 7, making it 9 by 7 mu actually. And that will be entirely with the second ball because the first one comes to rest. So divide by 2m to get the velocity. So you get 9 by 14 u.
Sir, why will it come to rest?
Why will it come to rest? Well, that happens because suitable. It's not exactly. Elastic collisions of identical bodies, but just happens to be the situation arranged in such a way, energy is being lost, and the forces which are present between them, it is the one which stops it effectively. What else? The dynamics is what forces it to stop. Why implies what? It will be difficult to predict in a very qualitative way. Qualitatively, it will be not easy to predict that it's going to come to rest. It just happens to be the mass are chosen in such a way, the velocity are chosen in such a way, it does come to rest. And also the E. E's factor is also important. Okay?
Okay, sir.
Yes, it's saying 9u by 14.
Yeah, that's fine. Can all of you access the WhatsApp? Just now, Sohar sent a page of a book. If you can see look at the question, which is, 10th question actually. 3 balls are there. Look at 10th question if you can see the WhatsApp. We just did 4th one. I'm looking at the 10th one actually. Okay, in any case, Sohar is presented as well. The screen. So the 10th question says there are 3 spheres whose masses are 2 kg, 6 kg, and it should be 12 kg actually. The masses are 2 kg, 6 kg, and 12 kg respectively. And the velocities are 12, 4, and 2 meters per second respectively again, which implies 2 kg is moving with 12 meter per second speed, 6 kg with 4 meter per second, and 12 kg with 2 meter per second. Each has momentum of 24 SI unit actually. They're moving on a straight line in the above order. If the coefficient of restriction be unity for all the collisions, show that the first 2 spheres will be brought to rest by collisions which will take place subsequently. To consider more than one collision over there, we have to just consider in this case that we have to just find out or prove rather that after all the collisions are over, the first 2 spheres they are going to come to rest, while the third one will be just moving with all the momentum available. Okay. In this case, the initial gap doesn't matter. You might, in this case, consider the collision any order actually. The first and second first collide, and whatever the result is, then the next one. You can do that like that. And we have to show that the first 2 spheres are going to come to rest. So you can do this. This question was done, I hope, by everyone. The question was wrote down. Somebody who is not able to do that? Maybe a bit more sleepy feeling. Nobody. Fine. Take the question number 10.
So can you show the previous question? I am not getting as V1 equals to
Okay.
0.
Just wait, the pen has jammed. In this case, it was said that we had mass m, moving speed u, and twice m, moving with u by 7. E was given to be 3 by 4. First of all, the momentum, subsequently, let's say the velocity for m, it is v1, while for 2m, it is v2. After the collision, so first of all, the momentum conservation, that gives us m into v1 plus twice m into v2 is equal to mu for this one and plus twice mu by 7 for the second one, which makes it 7 1 is 7 to 9 by 7 mu. M can be cancelled out, so you end up getting the equation V1 plus 2V2 equal to 9 by 7 u. That's the first equation you've got. Then the other equation is Newton's law of collision. That gives us Newton's law of collision. The separation speed, that is nothing but V2 minus V1. Separation implies this is going that way, this is going this way, so you can only separate if V2 is more than V1. So V2 minus V1 is separation speed. This must be equal to E times, that is 3 by 4 times. The approach speed is nothing but U minus U by 7. The approach speed. So that will give us the other equation, that is V2 minus V1 is equal to, it becomes 6 by 7. So we have to do a 4 to 3 is 6. I get 9 by 14. The second equation I've got. So use these equations, we can add 1 and 2. 1 plus 2, when I just add them up, I end up getting V1 plus 2V2 plus V2 minus V1, which implies 3V2. That is equal to 9 by 14 plus 9 by 7, which implies 27 by 7, 14 U, giving us V2 as 9 by 7, 9 by 14 U. But obviously, therefore, that V1 must be 0, isn't it? As we have. Okay.
Sir,
Hmm.
in the 10th question, the V1 is after first collision, V1 is coming 0 and V2 is
Mhm.
coming 8. And after second collision, V2 dash is coming, after second collision, V2 is coming 0. And V3 is coming 6 meter per second.
6 meter per second. The total momentum 24, 24, 24. That is 22 and plus 12. Yeah, that's fine. Okay. And if you got those, then you can just continue a couple of more. For example, so far things are moving in the same direction. So let's look at the question of 11th as well. 11th question. What is the answer? Last one. Last one. Abhirup, the first two spheres will come to rest. The third one, 12 kg one, will finally move with 6 meter per second. Okay. But three spheres collision. The first two will come to rest, while the third one, which is the 12 kg sphere, will continue to move with 6 meter per second.
So what is the coefficient of restitution? The value in question number 11? Is it half?
Yes, it is half actually. Half, yeah, it is half.
Question number 11, no angle of projection.
It is vertical. One is dropped, the other one is projected from the ground, straight forward. The ball is let fall from a height of 19.5 meters, and at the same time, an equal volume price of same mass actually is projected from the ground with a velocity of 39 meters per second to meet it in the direct impact. Return direct impact head on. So the coefficient of restitution be half. Find a time that elapsed after the impact before the ball reaches the ground. Before the both of them actually.
So sir, here the means formula will be V2 minus V1 equals to E into U2 plus U1. Means we have to add the
Yes.
initial.
Yes. If you just take a downward direction as positive, I mean, it hardly matters. The point is, yes, beginning they will approach each other, so the relatives will be added up to obtain the relative speed of the other speeds, and subsequently, assuming that the lower ball is moving, say down with a greater speed, it will be V2 minus V1. Okay.
What is the question? Understand?
Could understand.
No, sir.
Well, the question says what? It says that, in effect,
So I should have said projected directly upwards.
It is written. It's written. I mean, say, when it's from the ground with a velocity this much to meet it in a direct impact. It's written. It's a head-on collision. So it only
Yes.
happen if it just moves straight. Basically, there's a ball which is dropped from a certain height, which is 19.5 meters. Once the ball is dropped, and let's say this is A, and at the same time, another one from the ground is projected upwards with a speed which is given 39 meter per second, I believe. Yeah. It's useful in this case to take G as 9.8 actually meter per second square. This is projected at 39 meter per second. At the same time, this is dropped. So what will happen? They'll just this will fall, it'll go up, and at some point they collide. This collision is given to be having a coefficient of restitution equal to half. So we have to find out the time after that elapses after the impact, before the balls, which is much from here, from this moment onward, what time will be taken by each of the ball to reach the ground? There is a point. There is a question you're asking. Okay. So in effect, during the collision, you can simply neglect gravity. Just do the usual thing that we do for these two, this collision. Find out the speed of this B, assuming, well, let's consider this happens at a certain height h, for example, from the ground. So we can find the speed over there, and the speed is known as well in terms of h. Momentum conservation can be applied, and the coefficient of restitution. Subsequent speed can be figured out, and then we have to find out the time taken by these two balls to reach the ground. You're okay? Actually, the height can be obtained as well, seemingly. Whenever they meet, that can be figured out at what time they're meeting. It is easy enough because we can always consider the relative motion. So relative motion will,
So we
yes,
have to find the time to of collision.
yes, that has to be figured out, actually. I mean, at this point, just before the impact, we need to know what time has elapsed because I need to find the velocities of each of them. It can be done quite easily by considering the relative motion actually. We can simply consider the relative velocities because the relative acceleration is zero. So relative velocity remains a constant. You can just look at from the perspective of A. A didn't have any velocity to begin with. This has 39 meters per second. So as far as A is concerned, it seems that the ball B is moving with a speed of 39 meters per second towards it. So the time taken can be obtained by dividing 39 meters per second. I mean distance 19 or 19.5 it was, I believe. 19.5 meters by the speed 39 meters per second. That is what a time should elapse actually because the relative acceleration is zero, isn't it? Or you could just use the fact that the distance covered by
There we have to neglect the t.
which one? Why should neglect the speed? I was talking about the relative motion. Relative to A, B is going to be having no acceleration at all, isn't it?
Yes, sir.
So relative to A, B will have just a constant speed, the same which was initial, 39 meters per second towards A. So as far as A is concerned, what does A sees? A sees that B is moving towards it with a speed of 39 meters per second. Distance was 19.5 meters. You can find a time therefore. Or if you wish, you can just use the fact that this will be half gt square. While this displacement is going to be 39t minus half gt square. The sum total must be, if I add these two, I should get 19.5 meters, which is the same equation I'm getting. 39t becomes
0.5 second.
what?
The 0.5 second.
That is for the,
Time of collision.
yes. So once you know this, you can find what was the speeds of both the balls at that moment. That will be the velocities before the impact. I know. You also know the height at which the collision takes place. It's going to be just half into 9.8 into 0.5 square, which implies 1 by 4. So 9.8 0.54 meters is the distance traveled by the upper one. The one can be calculated. Just figure so we just know that after 0.5 second the collision takes place. So the velocities must be known for each of them before the impact, isn't it? That becomes a u. And then analyze the collision, assuming there's no gravity at least during the time of impact. Analyze the collision, and you could then figure out the final velocity as well. I mean, immediately after the impact, actually, that's what we want. Let's do this. Time we have already figured out for collision. 0.5 seconds. So I know at which point the collision is taking place. 39, it's half into 9.8 to 1/4. So it's around 1 point something, 1.25, I believe. How much it
So
is?
1.225.
That is what?
Sir,
1.25, yeah.
distance from A.
हाँ ठीक है 1.25 का is too much significant ठीक है not an issue and therefore I know the collision takes place somewhere over there. It has a velocity which is g into 0.5, which is 4.9 meter per second. It has a velocity at that point which is 4.9 meter per second. I can find the speed of B as well, 39 minus 4.9, which makes it how much? 34.1, isn't it?
So how you find the 4.9 meter per second?
V equal to U plus GT, U is 0, 9.8 into half, 0.5,
Yes, sir.
isn't it? Yeah. .1 meters is the meter per second is the speed for V. Maybe we could take in G as 10 itself, that would be useful. But take G as 10, that'll be better. Take G as 10. Otherwise, there's too much calculations not needed. Take G as 10 meter per second, this becomes 5 then. Time will obviously remain unchanged. This becomes 34 meter per second. We can now therefore analyze the collision just immediately after the impact. Say the velocities for the two balls immediately after the impact. They are VB and VA in a downward direction, I'm assuming. These are the velocities after the impact actually. Therefore, first of all, the momentum conservation. That gives us masses are identical in fact. So I get VB plus VA is same thing as I'm taking downward as positive. So I get 5 minus 34. That's one equation you have got for the momentum conservation working in SI units. Then the restitution one that says that the relative speed of separation speed is VB minus VA. That we E times E in this case is given to be half into the relative speed of approach, which is 34 plus 5 is 39. I've got these two equations. We can just add them up to get VB, twice VB, add in this case. So twice VB turns out to be 5 minus 34 is minus 29 plus 39 by 2. How much is that? 19.5 and 29. Subtract. Minus 29. plus 39/2 gives us minus 9.5. So VV is known. So VV is basically half of this. Minus 4.75 meters implies actually moving the upward direction after the impact. You'll just take the ball above with that. While VA can be obtained as uh, what minus 29 minus VB. So we know VA as well. There's also negative, which implies both of them are now moving upwards actually. Then it is like simply throw something at some height, goes up and then comes down. So that is the task you have to finish. Okay.
Can you explain the last part once? Means how did you derive the equations?
Which one? These two. I consider first the momentum. After the masses are identical actually, so I have just not taken them. You can just take them one, for example, or M will cancel out. MVB plus MVA is the initial downward momentum, and this one downward is 5 for the upper one, minus 34 for the lower one. Downward direction I'm considering, which is the motion of the two I have assumed. Okay, that is why we have got this equation. Second equation is from the collision, the relative speed of separation. Separation speed is uh, nothing but VV minus VA, and the approach speed is simply 39 meter per second, and E is given to be half. So we get that. Okay.
So why are we considering 5 as the initial speed of A?
Not initial, just before. Why? Because this was moving 5 meter per second because the collision takes place 0.5 second later, and this was in free fall. So G into T, G have taken as 10, so 10 into 0.5 is 5. Okay, or not okay?
So that's 47.5.
It is saying something.
Nothing. So understood.
Okay. You finish it later, okay? Finish it and take the homework. I mean, just finish it later, the homework. Okay? You can finish it now.
Sir,
Hmm?
sir, now please again what we have to find, what time?
The time from this moment, the collision to reaching the ground,
So both the balls.
both the balls.
So they will reach at the same time or separately.
Why should they be same time? They are moving. They are actually from the same height, but
Yes, sir.
then
We have
the
to find.
initial velocity are different.
Yes, sir. We have to find the time for each.
Time for both. A and B both. You see that A and B they had they're starting from this point in upward direction. They have initial speed which are unequal. For this one, well, we have calculated VB we know it's minus 4.75 and VA was also turning out to be upward. They are both say moving upward from that initial point, but they just have been projected from a different heights actually. Okay, sorry, same height but different initial speeds, and that is why the time will be different. Okay.
Yes, sir.
Okay.
Say initially what was the speed of B? 39 meter per second. Means while throwing, just
Yes,
throwing.
10 meters per second.
And sir, after the time means when they will collide, it will be 39 meter per second.
The relative speed of approach that will be 39 meters per second. They have to add the two speeds. Okay. Not okay.
Okay.
Okay, fine. That'll be all the
The
Huh. answer.
Yes, sir.
So how can you check the answer? At least the pages.